Hello and welcome everyone to EC3030. So in this video lecture we will be talking about the thermal aspects of computing. So essentially any power that is dissipated in a microprocessor chip is converted into heat. Now what this heat does is it increases the temperature of the microprocessor. Now if you increase the temperature of the microprocessor, the reliability goes down. And if the temperature is too high, then even the microprocessor can melt in the extreme cases. So essentially what we need to do is find a way to efficiently remove the heat that is generated, but the amount of heat that we can remove from a physical system is bound by physical constraints, meaning that the physics of heat transport limits us as to how much heat that we can remove or how efficiently we can remove the heat from a microprocessor. And that is essentially the crux of what we call the thermal wall. We have heat a region where we cannot remove as much heat as we want, and that is another bottleneck that computing is facing today. So we will look into this in more details in this video lecture. Alright, so again to understand what thermal wall means, let's get back to scaling. So we have been scaling our transistors and the density of transistors is increasing in our microprocessors. Now this is what we have seen in details when we were talking about Dennard scaling, but it happens so that for almost 2 decades, although we are increasing the transistor density by decreasing the dimensions, physical dimensions of the transistor, we could not reduce the power supply voltage as we wanted it to be, as much as we wanted. So in Dennard scaling, we have seen that if we could scale all the physical dimensions and the power supply voltage by a factor of x, then the power density would have remained the same. But also what we have seen is that if we reduce all the physical dimensions but not the power supply voltage, then the power density does not scale down. And as a result of this, because we have not been able to scale the power supply voltage almost 2 decades now, what has happened is that since 2005, the microprocessor clock frequency has been plateaued around 3 gigahertz. Why is that? If we have been increasing the clock frequency as we were doing before 2015, the power density in the CPU would have increased above the level of 100 watt per centimeter square. Now what would have happened? So why this limit of 100 watt per centimeter square? It happens so that this is the amount of heat that we can efficiently remove from a microprocessor chip. Now if we had increased the clock frequency like before, then by 2010 the power density would have reached that of rocket nozzle, and by now the temperature of the microprocessor chip would have reached that of the sun surface. So essentially what we are saying is that we had to stop increasing the clock frequency because we could not remove the heat as efficiently as we have wanted, and this is what is called the thermal wall. So thermal wall is closely related to power wall, or you can think that they essentially mean the same thing. So power wall, you can think about it like if you had increased the clock frequency, you would have the microprocessor would have required more power. So you don't want to put more power in the microprocessor because of two reasons. First, it simply dissipates too much energy, and second is that you could not have removed the heat efficiently, and that second point is called the thermal wall. Alright, so just to give you an example, what I'm showing here is a heat map of two microprocessors. One is the Pentium 3 processor that came out in 1999, and the other one is the Itanium processor, which came out in 2001. And based on what essentially the heat map shows is that the amount of heat you can see in this picture that there are hot spots in the microprocessor chip. So the hot spots are more prominent in the Itanium processor compared to that in the Pentium 3 processor. Now the heat maps do not have the same scale bar, but essentially what this image shows is that there are hot, significantly higher temperatures in the Itanium processor which came out later. So that gives you a sense as to what the heat problem is in a microprocessor. And another result of this thermal wall is what is called the dark silicon. Now it happens so that the amount of circuit in a microprocessor chip, so dark silicon means the amount of circuit in a microprocessor chip that can be powered on at the nominal voltage for a given power constraint. So just to give you an example of what it means, for example, in 2008, the 14 nanometer node processor, the entire chip could run at the same time at the nominal operating power supply voltage. But again, going forward in 2014, in the 22 nanometer, it happens so that only 1/4 of the chip can run at the nominal power supply voltage at a given time, meaning that at the same time the entire chip cannot be running at the full clock speed and the nominal power supply voltage. And it becomes even more dire at the 11 nanometer node at 2020, where only 10% of chip can run at the full clock speed and the nominal power supply voltage. Because if the entire chip runs at the full clock speed at the nominal power supply voltage, then it will generate too much power and the resulting heat can cause serious problems for the microprocessor chip. So just to give you an example where the power is dissipated in a computer. In other words, what is the power breakdown of a computer system? So here in this table, what I'm showing is what are the different components in a computer and how much power they dissipate nominally. For example, if you look at the CPU, it dissipates around 100 to 200 watts of power. So the CPU is here. And then the memory, so the memory is also the caches and the DRAMs. They take up about 25 watts. Then you have the hard drive, which takes around 10 to 15 watts. Then all the different components in the motherboard, 40 to 50 watts. And then the power, the fan, all these things dissipate 30 to 40 watts. In total, a computer, probably a PC, dissipates around 200 to 350 watts. Now let's do a sort of a back of the envelope calculation, going from a dissipation in a simple transistor and how the transistor power dissipation, active power dissipation, is related to the total power consumed by the microprocessor. So let's say you have a microprocessor that has a billion transistors, 10 power 9 transistors, and say the dimension of the transistor is 100 nanometer, the oxide thickness is 1 nanometer. So the capacitance of the gate capacitance of the transistors comes out to be around 90 attofarads. So atto is 10 power minus 18. Atto is 10 power minus 18. So if you just plug in the numbers, this is the value that you'll get. Say the nominal power supply voltage is 1 volt and the clock frequency is 1 gigahertz. Then the active power is CL VDD square F, as you have seen in one of the previous lectures. This will come out to be 90 nanowatts. So each transistor, if each of them runs at 1 gigahertz at a power supply voltage of 1 volt, each transistor will dissipate 90 nanowatts of power, and then you have 10 power 9 transistors. So you just multiply these two numbers, you will get a 90 watt number. So the total microprocessor with a billion transistors will dissipate 90 watts. Now this is a very crude calculation. It not necessarily reflects the complicated situations in a microprocessor, but it gives you an idea that this is the starting from a dissipation in a transistor, how the transistor dissipation affects the overall power consumed in a microprocessor. So again, just look at if you look at the current that a microprocessor chip draws is actually pretty large. Say for example, Intel Xeon processor 2015 came out in 2015. It consumes a power of 150 watts and the operating voltage is 1.3 volts. So the maximum current that it will draw from the power supply voltage can be as high as 120 amps. Now compare it to a welding machine. So this welding machine actually draws 60 amps of current. So if the welder draws, like CPU draws a current that is equivalent to the current drawn in a welder. Now of course the welder works at 120 volts, so the power that the welder consumes is significantly higher, but still the current that the CPU can draw is impressively high, right? So now let's introduce the concept of thermal design power. So first of all the power that the chip consumes is converted into heat. Now the thermal design power means the maximum amount of heat that the chip can generate that its cooling system can handle, meaning that the maximum amount of heat the cooling system can safely dissipate into the environment. Now it happens so that in modern microprocessor, as we have seen, cannot operate at their microprocessor clock frequency without reaching the thermal design power limit, meaning that if the entire microprocessor works at the maximum rated clock frequency, then it is very likely that it will reach its TDP limit, and the dark silicon that we have talked about earlier is essentially a testament to that fact. Now what we are going to see is what are the different solutions that we can come up with to deal with this thermal wall problem. Now we do not have a complete solution to the thermal wall problem, but there are different kinds of techniques that are applied to handle the heat generation in a microprocessor chip. Now there are two types of solution that we will be talking about. One is the physical solution, meaning that we want to design systems physically such that the heat can be removed as efficiently as possible, meaning that we want better cooling systems. And there are also techniques that are not physical, rather architectural, and that can also enable microprocessor chips to remain within the thermal design power limit. Right? So these are the two things that we're going to see. So first we will look into the physical solutions, and for that we will start a quick discussion about how to model the thermal aspects of a microprocessor. So the first thing that we are going to talk about is the specific heat. So specific heat is defined as the amount of heat that is required to raise the temperature of a material of unit mass by 1 degree. All right. So the unit of specific heat is joule per Kelvin per kilogram. All right. So another term that we will use is another quantity that we will use is thermal capacitance. So thermal capacitance is essentially the heat required to raise the temperature of a body by 1 degree Kelvin. So say you have a mass m, say your microprocessor has a mass of m, and its specific heat is Cm. So its thermal capacitance Ct will be mass multiplied with specific heat, or M multiplied with Cm. Okay. So now how is it related to the temperature? So say your microprocessor dissipates P amount of heat, and this is essentially converted into heat. So the P is equal to rate of increase of the heat generated, and this will be equal to Ct, the thermal capacitance, multiplied with the rate of increase of temperature. Okay. So the next thing that we need to understand is heat flow. So the law of heat flow says that the rate of flow of heat from one side of a body to the other side is proportional to the temperature difference between the two sides. It's proportional to the area of the cross section through which the heat flows, and inversely proportional to the thickness of the block that separates the two sides. All right. So let's say, for example, this is the side where you have the microprocessor, and this is the heatsink, and this is the other side, and the temperature of the other side is essentially the ambient temperature, or the temperature of the environment, and which we denote by TA, where A stands for ambient. And the temperature on the other side, the side in which the microprocessor is T. So you can consider T as the temperature of the microprocessor. All right. So as the law of heat flow says, so and the P is the heat that is the power that is dissipated in the microprocessor that is being converted into heat. So what we can say based on the law of heat flow is that P equals rate of generation of heat. So this is joule per Kelvin, joule per second, or watts. So this is proportional to the difference of temperature T minus TA. This is also proportional to the area and inversely proportional to the thickness, or the distance between the two sides. So thickness is this D. All right. So then we can simply say that, okay, P equals ddt of H equals a factor K, T minus TA multiplied with A over D. And what we usually, so this K is a parameter of this material over here. It's a property of this material. And what we can say is that P equals to ddt of H equals T minus TA over RT, and this RT is defined as the thermal resistance. So in the previous slide we have seen thermal capacitance, now we are seeing a thermal resistance, and this thermal resistance is just equal to D over KA. Right. Okay, so now let's look at a system where you have a microprocessor here, and then we have a heatsink. Now the heatsink, we have drawn it as a solid body, but in reality the heatsink will have a lot of fins, such that the area of effective surface area of the heatsink is much larger. All right. So now the microprocessor temperature is T, the ambient temperature, the outside temperature is TA. Now P is the amount of power that is dissipated by the microprocessor that is converted into heat. So now a part of this generated heat will go towards increasing the temperature of the microprocessor plus the heatsink, and a part of it will be just flow away from the system through this heatsink. Okay, and this is given by this term T minus TA over RT. Now usually the CT corresponds mostly, so the big fraction of CT comes from the microprocessor itself, And the reason is that usually the heat sink material has a very low thermal capacitance, because these heat sinks are made of materials that have a very low specific heat. So CT corresponds mostly to the thermal capacitance of the microprocessor material, silicon basically. All right, so now you have an equation where P equals CT multiplied with ddt of T, T being the temperature and the capital T being the temperature, plus T minus TA over RT. Now this is a differential equation, and if you solve it, you will get an equation like this. Okay. So now if you, so this is the full solution of this equation. Now if you look at steady state, meaning that the temperature of the microprocessor has reached an equilibrium, it does not change anymore as a function of time. So if that at steady state, the ddt of T, the temperature, will become 0, and if you put ddt equals to 0 over here, then the solution of this equation will come out to be like this. So the final temperature of the microprocessor is the ambient temperature plus the power dissipated multiplied with the thermal resistance RT. All right, so let's look at an example. Say we want to find out the temperature of the microprocessor with and without a heat sink. Now, without a heat sink, the thermal resistance will have a high value, and with a heat sink, the thermal resistance will have a small value. Now, the power generated is 20 watts, and the ambient temperature TA is say 26 degrees Celsius. So, without a heat sink, you will get 20 plus 20 multiplied with 10, 220 degrees Celsius. So, as you can see, without a heat sink, the thermal resistance is large, and as a result, without a heat sink, the microprocessor chip may reach as high a temperature as 220 degrees Celsius for this particular example. On the other hand, with a heat sink, the thermal resistance is low, and as a result, with a heat sink, the maximum temperature that the microprocessor will reach is 50 degrees Celsius, which is much smaller than the 220 degrees Celsius. So essentially this tells you is that if you have a heat sink, then it reduces the thermal resistance, and as a result the temperature rise can be much smaller. Now note that usually the maximum temperature that a microprocessor can operate is usually rated to be 85 degrees Celsius. All right. So now let's think about how much time does it take for the microprocessor system to reach the steady state temperature. Now if you look at the solution to this differential equation, you will see that this term over here is dependent on the time, and this is the time constant RT/CT, thermal resistance multiplied with the thermal capacitance. Now for example, for a CPU, the thermal resistance can be say 0.5 Kelvin per watts, and the thermal capacitance is say 0.03 joule per Kelvin, and then the thermal constant, time constant, will come out to be 0.15 seconds. So it essentially means that for this particular case, whatever the final steady state microprocessor temperature is, once you start the once the microprocessor starts running, you power up the microprocessor, it will take around 5 RT CT, which is equal to 0.75 temperature, around 750 milliseconds to reach the steady state temperature from the ambient temperature after you have start running the microprocessor. And typically the thermal time constants range between milliseconds and seconds. So what are the different solutions to the thermal to solve the thermal challenges. And of course, what you want to do is design a very good heatsink such that the power that is generated is efficiently flown into the ambient through this heatsink. So one of the things that you want to do in the heatsink is that you want to increase the surface area, and to increase the surface area you make a lot of fins in the heatsink. At the same time, you have this fin, the heatsink material has to have a high thermal conductivity and low thermal capacitance. So heatsink is a passive solution. You can also do active cooling by putting fans, and by putting a fan over the heatsink you remove the heat quicker, and that allows for the microprocessor to generate more heat. All right, so and an even more recent technique that a lot of research has been going on is to use microfluidic channel underneath or over the chip. So basically in this microfluidic channels that are shown here, some sort of coolant flows through all the time, and this type of active cooling allows for to more efficient removal of the heat. So for example, what we are showing here is that this is the chip, and on the top of the chip there is some coolants flowing, and that coolant efficiently tries to remove the heat as efficiently as possible. And for big data centers, the heat challenge is even more serious. And the thing is that to make the transistor work as efficiently as possible, and to limit the amount of heat that it can generate, usually there are a lot of cooling techniques that are applied in the data centers. Now if you want to cool down all these servers, that requires a lot of power as well. So to run those cooling systems at the massive scale, you need also very big power supplies, meaning that you want your own own generators that can essentially even power a mid-sized city. So this is also why that a lot of the data centers are actually located in the cooler parts of the world. For example, in this case, a lot of data centers are located in the Arctic Circle. Because of the low temperature, the amount of energy that you need to cool the data centers can be significantly low, because the ambient temperature itself is low. So you can dissipate the heat more efficiently if you make these data centers in the cooler regions of the world. All right, so now let's look into the architectural solutions. So to tackle the thermal issues, so one of the techniques is called DVFS. DVFS stands for dynamic voltage and frequency scaling, and this technique is utilized when the active power is more dominant. Now if you remember, there are different kinds of power that are dissipated in a logic block. So we have looked into active power or the dynamic power, and also we have looked into the static power or the leakage power. So DVFS is applied when the active power is the dominant source of power dissipation. Now what this DVFS takes advantage of is the fact that the delay is proportional to VDD. Now this is something that we have seen when we were talking about inverters. So the delay is proportional is inversely proportional to the VDD. On the other hand, the power is proportional to VDD squared. Okay. So delay being inversely proportional to VDD means that the clock frequency is proportional to VDD. All right. So let's look at an example as to where this DVFS technique can be applied. Say you have a logic system that operates like this. So logic block 1, the output of the logic block 1 is input to logic block 2 and logic block 3, and the output from the logic block 2 and logic block 3 are required for logic block 4. Okay. So now let's say once it gets an input, logic block 3 gets an input from logic block 1, it requires 300 cycles to perform the computation and give its output to logic block 4. On the other hand, logic block 2, once it gets input from logic block 1, it requires 200 cycles to do the computation. So now what will happen if you operate both logic block 2 and logic block 3 at the same VDD? What will happen is that after 200 cycle, logic block 2 will create the output and it will wait and do nothing for the next 100 cycles until the logic block 3 finishes its computation. So now what we can do is something interesting. Say the VDD, so say the logic block 3, the power supply voltage is VDD. Now what we can do is we can reduce the power supply voltage of logic block 2 to 2/3 of VDD, and essentially say the clock frequency for logic block 3 is F, and we can reduce the clock frequency of logic block 3 to 3/2 F. Now if the power supply voltage is reduced to 2/3 of a VDD, then the delay of the microprocessor will also increase, and as a result we need to reduce the frequency by 2/3 of reduce the clock frequency of logic block 2 to 2/3 F. All right. So now what will happen? So what will happen is that for 300 cycles, the amount of time that logic block 3 will need to finish these 300 cycles will be 300 over F. The total time required by a logic block 3 to complete these 300 cycles will be 300 over F. On the other hand, for logic block 2, operating at 2/3 of F will require 200 over 2/3 F equals 300 over F. So essentially what has happened is that by reducing the power supply voltage to 2/3 VDD and operating at 2/3 of F, now logic block 2 completes this 200 cycle computation in 300 over F amount of time, which is essentially same as the time that is required by logic block 3 to perform 300 cycles. All right. So now what do we gain by this? Now see that the power that this block will now require is C 2/3 of VDD squared multiplied with 2/3 of F. So essentially you will need this amount of power will be dissipated by logic block 2. So what is the total amount of energy? So the total amount of energy that it will dissipate will be CVDD squared F 8 over 27 multiplied with the time, which is 300 over F. Alright. On the other hand, so say this is the power that you have dissipated if you have followed DVFS. So this is the energy that you dissipate when you have applied DVFS. On the other hand, if you did not do DVFS, then the total amount of power that you have dissipated, total amount of power would have been CVDD square F in logic block 2, and the total amount of energy would have been CVDD squared F multiplied with 200 over F. Okay. So now you can clearly see that this EDVFS is smaller than E, meaning that by slowing this logic block 2, you are now dissipating less amount of energy in doing the same computation. So what does it mean? It means that by following DVFS, you slow down certain logic blocks, and in doing so, you reduce the power consumption in that logic block. So this is one of the architectural solutions as to how you can reduce power dissipation or the energy dissipation when the active power is the most dominant source of power dissipation or energy dissipation. Alright, so now let's look into another solution, and that solution is called race to dark or RTD. Now compared to DVFS, RTD or race to dark is utilized when off-state leakage is the most dominant power dissipation mechanism. Now in DVFS, the dominant power mechanism is active power or switching power. In RTD, the dominant power dissipation mechanism is off-state leakage. And in RTD, what is done is run the block that you want to as fast as possible and then completely shut off that block, meaning that you just turn off that block. Now what is the off-state power dissipation due to the off-state leakage? Now off-state leakage power dissipation due to off-state leakage is also called static power, and as we have seen, static power is simply VDD multiplied with I off. Alright, so let's say in this particular case both logic block 2 and logic, so say you're in this case this logic block 2 requires 300 cycles, right, and this one requires 200 cycles to compute, and it runs at VDD. Okay, so say this logic block, the dominant power supply is not active power or switching power, rather the static power or the off-state leakage power is the dominant one. So what you would want to do is, rather than running at VDD voltage and frequency of F, let's say you run it at 300 over 200 or 3 by 2 F frequency, and to do that you have to increase the power supply voltage to VDD, and if you do increase the frequency to 2/3 of VDD, the total amount of time that you will need is 300 over 3 over 2 F, which is 200 over F. So you overclock it, and in doing so you perform the computation quickly rather than over 300 over f amount of time. Now you perform the computation over a time of 200 over f, and after you have done this computation, what you do is you completely shut off this block, meaning that you put the power supply voltage to 0 for this logic block, and in doing so you have now completely reduced the static power dissipation in this logic block. Again, what raise to dark does is, once you need to do some computation, you turn on a logic block, overclock it, do the computation as fast as possible, then shut it off, and in doing so you significantly reduce the static power.